Good afternoon. I'm Jay Scott, editor of ASHRAE Journal. Thank you for joining us for today's webinar, part of the Journal Supplier webinar series, providing information to readers and others about products and technology for industry professionals. ASHRAE does not review supplier webinar presentations. Schebler Chimney Systems has prepared today's webinar, High Efficiency Boiler Exhaust Venting. Today's presenter is Michael Mommsen. Michael has been with Schebler since 2008, providing technical consultation to engineering firms, building owners, and boiler manufacturers. Prior to Schebler, Michael spent 10 years as a systems build technician, programming engineer, and technical sales director for a major robotic welding systems integrator. Since his arrival at Schebler, Michael has worked extensively with experienced engineering and design staff to communicate and coordinate design practices that meet ASHRAE, IMC, NFPA, and ANSI requirements. Michael has also developed relationships with boiler HWH manufacturers to assist engineers in designing venting systems specifically for complex high-efficiency appliances. And now we turn the webinar over to Michael. Thank you.
Good afternoon. Today we're going to talk about the impact that venting systems have on boiler and hot water heater efficiency, which can impact the cost of operation for building owners and occupants, and also how that design impacts the efficiency and the cost to operate these appliances. We'll start with some questions here. First of all, what are the key differences in non-condensing versus condensing exhaust systems? You may know the difference between the boiler and hot water heater functions from condensing to non-condensing, but what do we really know about the exhaust venting system? Do the venting system design principles we have used for decades on non-condensing boilers and hot water heaters apply? While they may apply, we may need to definitely consider the modifications that need to be made to match up with today's high-efficiency appliances. Next question is, how does the design of these systems impact the performance of high-efficiency condensing boilers and hot water heaters? We'll discuss that at length. And then lastly, how do you properly design a system when common venting is required? It seems to be a very big concern in our industry today with a lot of different methods that are being utilized. And we're going to discuss the various methods and how they affect systems and what works and doesn't work. Well, we could spend basically hours covering the different codes on chimneys and vents and the different terminologies. Today we're going to really get down to some basics and discuss how the basics apply to a properly functioning system. NFPA 211, which covers chimney and vents, NFPA 54, and National Fuel Gas Code, they really provide us very little information on the design for proper operation. They really push the design for high-efficiency appliances off to the boiler manufacturers or the vent manufacturers. They may provide some safety guidelines that must be followed and do's and don'ts on applying products to specific applications. But even National Fuel Gas Code really provides us little information on proper design for Category 4 appliances. Pretty much provides us a lot of detail on Category 1 or atmospheric type appliances that burn natural gas or propane, but not much on high-efficiency condensing appliances. So I'm going to start real quick with talking about the boiler venting categories as a starting point for a system. So really this chart is published by National Fuel Gas Code. I'm sure you may all recognize this before. But what it represents from right to left is static pressure inside the vent. Left-hand side is negative, the center line is neutral, right-hand side is positive. And then from top to bottom, what the chart represents is the exhaust gas temperature inside that vent. Exhaust gas temperature below the center line, exhaust gas temperature above the dew point, so we're not condensing in the vent system. Exhaust gas temperature that's low, below the center line or below dew point, would be condensing. So if we look at a Category 1 appliance up in the left-hand corner, an appliance that operates in a non-positive pressure scenario, the exhaust gas temperature above the dew point, so we're not condensing, This would be your B-vent type appliance or atmospheric vent appliance with the hooded or shrouded connection to that appliance. Category 2 appliance, which there's really nothing I know of in the market right now that operates solely as a Category 2, but it would operate a non-positive pressure scenario inside the vent system, but exhaust gas temperature below the dew point, so it would be producing condensate in the venting system. Because of this because the system would produce condensate, we would deem that as a special gas van type system, and it would have to have a proper UL-listed product to match that operation mode. Category 3 appliance, positive pressure scenario, possibly anyway, inside the venting system, exhaust gas temperature above dew point. This would be your forced draft boilers, maybe your steam boilers. We would categorize those by NFPA as a building heating appliance chimney, it's kind of defined as, or a positive pressure chimney where they'd operate potentially in a positive pressure mode. And last but not least, we'll talk a lot about today is Category 4 boilers and hot water heaters. Operate with a positive pressure, hopefully, in the vent system and an exhaust gas temperature that is below the dew point, so we're condensing inside that system. We're going to talk a quick note on product application for the various categories. A type B vent appliance, which would require a UL 441 vent attached to it, could only be utilized as a Category 1 type appliance. If you're trying to apply that UL 441 product to a Category 3 boiler or Category 4 or Category 2, you obviously run into some serious issues. It can't handle positive pressure, it would leak. Can't handle corrosive condensate, so it would deteriorate rapidly. So from a sheer safety concern, you'd have to make sure you didn't specify a B-vent product and find out that it's being applied to a positive pressure Category boiler or hot water heater. Now, a Category 3 vent system, which would fall under UL listing 103 or 103 HT, which is high temp, building heating appliance chimney or positive pressure chimney, can work in a positive pressure scenario, but can also work in a negative scenario. So while from a cost standpoint, you might necessarily want to apply a 103 listed product to a Category 1 appliance, from a safety standpoint and functionality standpoint, that product would work just fine on a Category 1 appliance. Although it may not be priced appropriately, from a safety aspect, you would definitely be covered. Now, on UL 1738 listed product, which is deemed designated as special gas vent, it's designed to handle positive, neutral, and negative pressures. So theoretically, as long as you had an exhaust gas temperature on a Category 1 or 3 appliance that didn't go beyond the threshold of the UL 1738 listing, which UL typically I think has temperatures at 480 or maybe 550 for a maximum listing, and you apply those products to it, you wouldn't come in any serious risk of damage to the product or leaking exhaust gas out of the vent system. Maybe a pricing overkill, but from a safety standpoint, you wouldn't run into an issue. Because it's categorized as negative or neutral pressures, you would definitely apply a special gas vent product, not only to a Category 4 appliance, but a Category 2, because it's designed to handle corrosive condensate, and also is positive pressure, so we can also seal that condensate in the system, even though the stack or venting system may be under a negative pressure. While we're talking about pressure, let's talk about static pressure in a vent, which is listed on that chart. Static pressure in a vent can also be, or should be thought of as outlet pressure of the appliance. And when we talk about common venting system, we're going to hit a lot on outlet pressure, not just static pressure in the vent, because they're not necessarily going to be equal. But we're going to measure that static pressure in inches of water column. And what's going to affect that static pressure is going to be natural draft, which is basically the temperature differential of the exhaust gas temperature versus the ambient temperature. So the greater the differential, the more draft that's available. As those numbers become closer together, the less draft that's available. The height of the stack that we're attached to, the diameter has an impact on the natural draft, and also barometric pressure plays an impact to that as well. Altitude, barometric change in pressures outside based on weather can impact the amount of natural draft that's available. we always have to remember when we're looking at pre-designing a system and doing engineering work that natural draft is not going to be constant. It's going to constantly vary based on these factors. The static pressure event is also going to be based on the volume of exhaust gas flow from the appliance. And that's going to vary as appliance goes from high fire to low fire, or even from specific manufacturer to manufacturer. What is that volume of flow rate from the appliance? And then last but not least, what's going to affect the pressure event would be the draft loss. Basically the loss of flow of natural draft through the vent. So the configuration of the horizontal run, the breeching, length of it, diameter is going to impact the static pressure event. The offsets that we would have, not only in the horizontal, but also if there's offsets in the vertical stack. The friction loss, so the material selection, the design of the gores in the elbows or tees would affect that as a friction loss. And then the termination of the stack would have a specific loss characteristic to it that would need to be factored in to know what the actual static pressure of the vent would be. So when we talk about comparing design methods from non-condensing boilers to condensing boilers, we'll talk about basic sizing calculation that will be applied to a Category 1 or Category 3 appliance. The goal is always to ensure we have adequate exhaust flow under all conditions. And these non-efficient appliances, we've got some typically pretty high exhaust gas temperatures, so we've got a lot of natural draft available. But we're going to look at the sizing calculation at the boiler hot water heater with it at high fire, with it at high ambient temperature. The higher the ambient temperature, the less natural draft available, which is the worst case draft scenario. So we've got to make sure we've got high ambient temperature. We're still trying to operate these boilers. Are we still getting the full BTUs out of them? So make sure the system can handle the full BTUs. We're going to typically target slightly negative outlet pressures or stack pressure. Even though we're talking about Category 3 boilers, a lot of times our target range for outlet pressure, stack pressure is going to be slightly negative. And as more natural drafts available, excessive draft is very easy to handle on a Category 1 or 3 appliance. Category 1 appliances have a shrouded connection to the vent. They're relying on that to initiate exhaust flow anyway. But as we have more draft available than the appliance really needs, instead of pulling the air out of that boiler hot water heater, we'll pull it out of the mechanical room. And then we'll apply that same principle to a Category 3 appliance if we have too much draft by adding a barometric damper in the system. So we've got a sealed connection to the boiler, but the barometric damper allows us a passageway from air in the mechanical room to go up the stack based on how we adjust that barometric damper, so we don't pull a bunch of air through the boiler more than it can handle. Now we're going to start diving into design for Category 4 appliances, but a Category 4 boiler hot water heater is technically only a Category 4 appliance when it's operating in a positive pressure scenario at the appliance outlet and exhaust gas temperature below dew point. If my return water temperatures on a high-efficiency boiler hot water heater are set too high, okay, I can easily have my exhaust gas temperature go above the dew point and fall out of condensing mode, which means technically now I'm operating as a Category 3. I think we saw this a lot in industry. Replacement boilers in an old facility, none of the piping was redone. We had some extremely high return water temperatures in our condensing boilers, never really condensed and never operated as Category 4. So that's a common scenario. Also, if the outlet pressure or stack pressure goes negative on a Category 4 appliance, it's no longer technically operating as a Category 4. It's operating as a Category 2 appliance. And we'll talk about how that can impact our performance.
Slightly negative again.
Okay. By slightly negative, I'm going to be talking tenths of an inch of water column. So by slightly negative, 0 would be neutral. If I am a minus 0.001 or minus 0.01, I would consider that to be slightly negative. We had a question here. Why do we want our high-efficiency appliances to condense? What's the whole purpose of condensing? You may know this, but the whole purpose of condensing high-efficiency appliances is to obtain latent heat from the vaporization. So the condensing of water vapor and exhaust gas basically of combustion releases useful heat and improves our efficiency. And the amount of heat that we're going to be able to capture is going to be based on the type of fuel. So natural gas is going to probably do more. Propane is another gas fuel that we're probably going to be able to condense a lot. you see condensing or near condensing fuel oil boilers. So that's going to affect how much we can condense. The air-to-fuel ratio plays a big impact, how lean or how rich that air mixture is on how much we're going to condense. And we talked about this, the dew point, the exhaust gas temperature plays a big factor. Exhaust gas temperature is too high, we're not able to condense, we're not able to achieve that efficiency, okay? What we really want to say is the more we are condensing on a high-efficiency blowout water heater, the more condensing we have in the exhaust system, which basically means the more efficiency we're getting in the appliance. So talking to high-efficiency appliances to reach their published 95, 98% efficiency, we can produce, gallons of condensate an hour. So we want to talk about how vent pressure can affect all this. So we're going to start with the sizing calculations for Category 4 appliance and how that can differ from a Category 1 or 3. But what's really key on a Category 4 appliance is to make sure we apply specific appliance information. The market is full of various manufacturers, various models of boiler and hot water heaters, and each one can have this distinct characteristics that we have to make sure our system can be designed to match. Even sometimes from manufacturer to manufacturer, from model to model, it can vary. So we need to take a close look at what is the turn down ratio. We're seeing 5 to 1, 10 to 1, 20 to 1, 25 to 1 turn down ratios. That plays a factor in how we do our sizing calculation. Outlet pressure, almost every manufacturer of a boiler hot water heater will publish what exhaust outlet pressure range they're designed to reside in for flame stability and efficiency. And we want to know what that is when we're doing those sizing calculations. The outlet diameters can vary from model to model, manufacturer to manufacturer. I could have models of the same BTU output with 2 inches difference in diameter of the exhaust, which would factor in how I do my exhaust system because I have to typically size my exhaust out of the boiler the same diameter or larger to be able to keep that boiler certification. And also there's going to be specific operational characteristics we may have to pay attention to as well. So it definitely makes sense to know that manufacturer's installation operation manuals, make sure we match it. The other thing we pay attention to in the sizing calculations is the ambient temperature. We're in Iowa, so we're dealing with 0 and sub-zero temperatures this week, but that's going to play a factor when I'm looking at the natural draft and sizing calculations. Hence, will make a difference if I'm designing a system in Florida or Arizona where my average daytime low temperature, may only be in the middle of winter, in the 30s versus sizing for somewhere where we may look at 0 or sub-zero type temperatures. So we're going to go through a design scenario for a Category 1, Category 4 system, a sizing calculation. And for this design scenario, I selected a 2 million BTU boiler. This particular manufacturer model I selected had an 8-inch exhaust outlet on it. The turn down ratio on this appliance was a 10 to 1 turn down ratio, and the manufacturer's published exhaust outlet pressure range was a positive 0.40 inches of water column, and the max negative is a minus 0.10 inches of water column. If you look at this design scenario, I have roughly 50 feet of vertical stack and 25 feet of horizontal. So we've got about a 2 to 1 rise-to-1 ratio in the breaching to stack. So number one, we're always concerned with is this diameter large enough to make sure we get the full BTUs out of this boiler on a poor draft condition scenario. So for this design example, this boiler has a maximum exhaust flow rate of 425 cubic feet per minute. At full fire, we select 130 degrees for the exhaust gas temperature, which gets us well in the condensing mode. And we select an ambient temperature for worst case draft scenario that we may need to require building heat at 65 degrees above zero. So for this particular boiler, 8-inch outlet, full fire, 65 degrees, the outlet pressure in inches of water column is a positive 0.2350. So we have Category 4 operation, and we're inside the maximum outlet pressure requirement published by this manufacturer. So step one is good. Looks like we're in good shape. Now we're going to start looking at the low temperature operation. This same boiler at high fire, and I selected 0 degrees, trying to match today's outside temperature here. And at full firing rate, the outlet pressure drops significantly, but still on the positive side, so we still have Category 4 operation. and still within the manufacturer's requirement. So right now at full fire 0, we're at a positive 0.1322. What happens though when we start modulating this boiler down to a lower firing rate? So this next scenario here, we've got the boiler at its lowest firing rate. So our exhaust output is 43 CFMs. I still retain 130 exhaust gas temperature. It may or may not drop slightly. But I still selected the 65-degree ambient temperature day. You can see even at 65-degree ambient temperature day on low firing rate, the outlet pressure goes negative into a Cat 2 operation. I marked it as yellow because it's not outside the operational requirements of this appliance, but we're getting close to it at a minus 0.0757. So you can imagine now when I take the outside air temperature down to 0 degrees and I've got more draft available, this boiler at the same low firing rate, my outlet pressures go, in this case, to a minus 0.1786, which is fully in Category 2 operation mode, and below the outlet pressure requirement of that manufacturer. So really, do we really know what happens in a case where we start falling so far negative? What really happens is we have an impact on efficiency. Category 4 high-efficiency blown hot water heaters are designed to have approximately 5 to 10% of excess air above the perfect air-to-fuel ratio of stoichiometric combustion to meet their peak efficiency. So we've got a window to reside in of excess air that we need to be achieving our maximum efficiency. If we go beyond that, what happens is excessive draft really creates excessive air. So we really technically have heat loss out the vent. So as we see the natural draft increase and the outlet pressure of the appliance go more and more negative, we cross over into Category 2 operation, which automatically reduces our efficiency. But as we keep going farther and farther negative, we keep pulling more and more heat out of that boiler, so we constantly reduce its ability to retain its efficiency that it's published at. So anytime we get into Category 2 basics, we're basically not going to be able to achieve the published efficiencies just because of the vent system, because of no other factors. So it plays a very important factor in designing a system to try to operate in Category 4 mode as much as possible, not only just to make sure the boiler operates properly, but to minimize any heat loss up the stack. Also, as we fall outside of the appliance manufacturer's published outlet pressure ranges, we start having issues with the boiler. We start having alarm and air factors, okay? Ignition failures. Let's say this boiler scenario wasn't on and we try to light it. Even though the boiler's not running, we're still going to have a stack effect of air being pulled through that boiler and up the stack. So if I'm fairly negative at the outlet and we try to light this appliance, I'm going to have a hard time getting it to light. And it's going to be more prevalent on cold weather days. And, in the Midwest here, it's going to be about 0 today. It's going to be probably 40 this weekend. That ignition failure problem might not be prevalent once it's 40 degrees outside because I've reduced the amount of natural draft available, and now my pressure in the stack or outlet is higher, and I don't have an issue lighting it. Also, flame failure. With the high modulation rate, it's sometimes harder to get a stable flame. And as we look at excessive negative outlet pressures, it's really hard to get flame stability at lower firing rates. And you can have these boilers have flame failures when they go into low firing mode on low temperature conditions. So the problem is it becomes an issue that looks like it's a boiler problem, and it looks like it's a very intermittent boiler problem, when really it's a result of improper stack design being applied to that boiler hot water heater. Okay, it's pretty uncommon to have a single boiler fall outside the pressure range. I showed you one example there. You always want to check that. But it becomes more concerning when you talk about common venting, high-efficiency blown hot water heaters. And so the question is, if I can have a problem on a single vented system, why do I want to even try to tackle common venting? Well, here are the reasons why you might need a common vent. One may be you've got an existing chimney in an old building and you're putting new boilers in. I only have one way out of the building with my exhaust. That's going to force me to common vent unless I can just dump it off the side of the building. The mechanical room space it may take, if I've got multiple appliances in a mechanical room, the venting can take a significant amount of space. We used to look at these buildings where you have 1 or 2 large boilers supplying heat for the entire building. now the design philosophy is multiple smaller units, and we bring those online as the demand for heat in the building increases, and are able to turn them off as it decreases. So we're able not only to have high efficiency boiler, but able only run the ones we need based on the demand of the building. So we're talking of a lot more small units than we were in the past, so it means a lot more individual vent runs if we're not going to tie them into a common. By tying them together, we can lower our material cost as well. I don't have all those individual 6 or 8 inch vents. And then also installation cost. All those individual vent systems that have to run through the building or up the side of the building can have a significant initial impact on cost. So what is the concern when I start common venting high efficiency appliance? Number one is a safety concern. So now I'm tying multiple appliances into one exhaust system, and I hit this a minute ago. We might not be running these appliances all at the same time. So I've got a real safety concern. You know, can I eliminate any risk of downdraft in an unfired appliance? Secondly is performance issues. I'm tying them all into a common vent system now that's really designed to handle all the appliances running. You know, can I get proper trouble-free operation tied to a common? And then secondly, can I achieve the maximum efficiency of that boiler hot water heater if it's tied into a common? So number one on safety, common vented system. You know, I've got byproducts of combustion here that I've got to make sure I can safely exhaust from the building. So I've got to make sure I've got adequate exhaust flow all times under all conditions. And if I don't have enough natural draft, I may need to do a draft inducer to make sure that can happen. I have to make sure I can handle all boiler hot water heaters at high fire at a high ambient temperature. So I want to make sure I can get all the BTUs out of the boiler hot water heaters I'm putting in a building under a poor draft condition scenario. And then I also have to make sure always that I have no backdraft through unfired appliances. So one method of this upper sizing would be to apply almost like we did for an individual vent system to a common vented system. And we see this a lot as a old Cat 3 or Cat 1 method of sizing a common system. So what they would do is take the combined CFMs of all the appliances tied into the breaching and stack, factor in a loss for the entire system. So every fitting in the system, change in direction, and then calculate the amount of natural draft that's available based on, you know, stack height, the other factors. But when we do that on a breaching and stack pressure method, our only output we have is what is the actual pressure in that breaching or in the stack. And because of that, and because we have the risk of having boiler hot water heaters off in the system, it's going to be desized to where the breaching is negative at all times, which basically means we're going to be in Cat 4 operation at all times and in all conditions. Because, again, we've got to make sure we don't have any backdraft through unfired appliances. So really not the best sizing method when I'm looking at common venting high-efficiency appliances. Another method that we see out there a lot, and I think this is really driven by boiler and hot water heater manufacturers certification, they're typically tied into a maximum number of linear feet that they can vent with those appliances. But when we use that for a sizing method for the appliance, it doesn't give us much accuracy. So what happens here basically is we have a total run length of the entire exhaust system, and the manufacturer is going to publish a minimum, but more than likely a maximum total of linear feet that they will find allowable, and kind of use that as a go, no-go gauge for the venting system design. So they take the number of feet of horizontal, number of feet of vertical stack. They would apply a set number of linear feet to fittings, so elbows, 90-degree elbows, 45-degree elbows, junctions in the system, and come up with a total system length. From that length, we're able to subtract the amount of natural draft, so there'd be a calculation to say, okay, based on the exhaust gas temperature, ambient temperature, and height and diameter of the stack, we can subtract so much for natural draft, but come up with the total run length. Like I said, it will give us a go or no-go gauge to say whether the system works or not. The biggest problem is it doesn't satisfy the knowledge of what is the outlet pressure going to be in those appliances, and can we stay in those ranges as we change the operating conditions or firing rates or ambient temperatures. Well, what we feel is a better method to ensure proper operation would be to do a sizing or pressure drop calculation that would give us the net result of what is the outlet pressure at each one of the appliances tied into a common. This will allow us to account for changes in velocity, or basically, diameters as we go into the main breaching. It will allow us to look at the flow rate from the appliance and be able to determine what happens as we change that flow rate of the appliance. Would allow us to equalize the pressures for appliances tied into a common, and make sure that we can satisfy the pressure ranges that manufacturers publish. So the design example I'm going to kind of show you here is 3 boilers tied into a common. This obviously is not quite to scale here, but it's kind of hard to fit on the screen. So we'll go through the first design scenario. These again are 2 million BTU condenser boilers tied into a common. We have the same high flow rate of 425 cubic feet per minute at full firing rate. We looked at 130 degrees exhaust gas temperature, and to make sure this vent and stack were large enough to handle it, we looked at the sizing scenario with 65 degree ambient temperature. So all boilers full fire, 65 degrees outside. Outlet pressures, boiler 1 is 0.26, boiler 2 is 0.25, and boiler 3 is 0.194. So if the same outlet pressure requirements were a 0.4 inch positive to a minus 0.1, as far as a negative, we fall inside the range in that scenario. Now, to make sure we don't have draft or unfired appliances, the next thing we have to make sure we look at is if I turn a boiler off in a poor draft scenario and the other ones are still at full fire, will that off boiler go negative at the outlet to make sure we don't have draft coming back down through it? So in this scenario here, I took boiler 1 off, left boiler 2 and 3 at full fire. Boiler 1, by the way, had the highest positive pressure. And as we see here, at 65 degrees, boiler 1 outlet goes minus 0.0388. So this in essence is telling me I've got enough flow under all conditions to make sure I don't have draft coming back through unfired appliances. Before we go any further, we get told a lot about draft induction fans. What about draft induction fans? Shouldn't we be using this on all common vented systems? It's kind of become a little bit of an industry standard or thought process when I tie into a common to make sure I don't have draft or unfired appliance, or to make sure I get flow at all time. If I put a fan in the system, it's going to cure any problems I would have. Well, the one note I really want to make on draft induction fan is its purpose is to create draft. It's really not designed to control necessarily the outlet pressure of each one of those appliances. So while it will ensure flow under all operating conditions, if I have enough natural draft available in my system because I can have a large enough stack height, large enough diameter, an exhaust fan in essence basically is just adding cost. It's adding reliability concerns because now if I lose the fan, I lose all the boilers tied to that one main breaching and stack. So while draft fans have their place, if I have a short vertical stack height or maybe a straight horizontal termination, really their whole goal is to simulate natural draft that's not there, not necessarily be an outlet pressure control mechanism. So kind of want to go back to our sizing scenario. We're going to go back now and start looking at low ambient temperature conditions, more natural draft available. The same calculation, all appliances at high fire, 0 ambient temperature outside. If you look here, the outlet pressure still remain positive. We still have category 4 operation. We're at full fire, even though our outside air temperature is at 0. So far we're looking good, achieving some efficiency and still inside operation ranges. What makes it tough, though, is obviously we're going to have boilers at different firing rates based on what the demand of the building is. Very seldom do I see the plan to operate high-efficiency boilers is to have them all at a consistent firing rate all the time. So for this design scenario, we've got boiler 1 now at low fire. Boiler 2 is at a mid-fire. Boiler 3 is at high fire, and an outside air temperature of 0 degrees outside. Note all the outlet pressures go negative, so we're at category 2 operation, and actually they all go below the max published negative that's allowed by the appliance manufacturer of a minus 0.01. And one last of the design scenarios, even at a 25-degree ambient temperature day, let's say I have two appliances running, one at high fire, one at 25% fire, I still see the outlet pressure of lower firing appliances go outside the operational ranges. So this is the biggest fear you have when you common vent, is seeing the outlet pressure variance and swings, and seeing all basically running as Category 2 instead of Category 3. So what happens if we decide to apply a fan, like I talked about a minute ago, the system, and try to utilize that as a mechanism to control pressure, not just induce natural draft? Well, we kind of tweaked our program here. If we were going to put a draft induction fan in a common vented system, the fan would have to maintain or have a pressure setting at a negative, a slightly negative, on the breaching stack at all times to eliminate the risk of draft from an unfired appliance. So by adjusting my calculation, have the breaching pressure slight negative. In this case, we just went a minus 0.0489, so basically almost a minus 0.05. The outlet pressure of the appliance that are running that system would be equal to or more, would be still very negative. Low firing appliance at a minus 0.11, mid fire at a minus 0.08, and a high fire at a 0.02. So the minute we try to utilize a fan as an outlet pressure control, we're automatically going to be operating in Cat 2, and we're still really going to have that risk of having outlet pressures go below the manufacturer's required max negative. Again, we're also a Cat 2 operation going to have, heat loss through the stack, reduced efficiency, possible flame failures, boiler alarms, and so forth, because we're right in that fine line. We're in Category 2 mode to being just staying negative enough to make sure it works and not going so far negative that we're going to, in fact, impact the ability of this appliance to operate properly. So how do I control? How do I control on a common vented system? How do I adequately control it? One method that's been utilized has been locking conduit dampers or locking or blast gate dampers at the outlet of each appliance. And what will happen with that damper is when the boiler's hot water heaters be started up, they would adjust that damper to basically not have excessive draft when that boiler's running. So if you're here in Iowa today and you're starting up a boiler and you've got to lock quite a damper in, you'd have quite a bit of a natural draft available. You'd probably have that damper quite a ways closed. You'd lock in position. The boiler can probably go through its paces and probably operate okay based on the damper in the position. But the problem is that damper's in a fixed spot. So a week from now, it's 40 degrees outside. You're going to find that damper is going to be too far closed. So now what happens is I've got a block fluid condition because my boiler can't ramp up to a higher firing rate because the damper's too far closed. So you go back and you adjust the damper again. It's really better probably than no draft regulation at all, but the problem is you seem like you never find this damper in the correct position to get proper operation, high fire, low fire, and through the various temperature ranges that you're dealing with. Well, what if we just throw a barometric damper and like we could do on a category, maybe a Category 3 boiler that operates in a negative scenario or operates as Category 1. In essence, what a barometric damper would do allow us to pull air out of the room instead of through the boiler. But if I apply it to a Category 4 appliance that truly can go positive, that damper's not made to seal if my stack pressure goes positive and I dump exhaust gas back in the mechanical room. Hence, you can always also leak condensate back in the room, which is a problem as well. So while I've seen barometric dampers try to be applied, I've also seen the problem with the barometric damper basically spitting exhaust gas back in the mechanical room, and it does not fix the excessive draft problem. So a method Schebler has been using to control excessive draft, especially on common vented systems, is sequence draft control. And in essence, what we're doing is we're monitoring and controlling the outlet pressure of each one of the appliances independently. So we're basically taking a pressure reading at the boiler outlet and running an actuated damper to stay inside a preset pressure range that coincides with the manufacturer's outlet pressure requirements. That damper is going to be closed when appliance off, so we don't pull air through an unfired appliance. We'll go through a startup sequence, so we're not two-part open to affect flame stability startup. And it allows for individual settings. So while I could have maybe boiling hot water heaters tied in the same common with two different outlet pressures, I can have each one of those dampers set to stay inside the pressure rating required. Another key factor with this damper system is while our breaching and stack could go excessively negative, by controlling the outlet pressure, I can have the outlet pressure positive on all of my appliances at any point in time to make sure I'm achieving maximum efficiency. Going to just show you a couple of design examples here quick. This example of a project we did in Colorado, 8 condensing boilers, as well as tying in 2 vertical tube steam boilers. This was new construction, and we had a tall vertical stack height and could pretty much set what diameter breaching and stack we needed to be. But there was no need for a draft induction fan because we had adequate natural draft under all conditions. But you can imagine with that many appliances in there, as we start shutting appliances off or just bringing them online when needed, we've got more natural draft than available. So this particular system utilized our sequence draft control dampers at each outlet of each appliance and allowed us to maintain a positive outlet pressure on each one of those appliances, even though our stack and breaching would be very far negative on cold conditions. Also, the fact that we're controlling them each independently allowed us to tie in the steam boilers as well. They had economizers on, which took stack temperature inside of our UL 1738 listing into the same breaching and stack. So what this project allowed us to do was save a lot of material cost for the building owner, save a ton of space in the mechanical room, and then 10 roof penetrations, 10 vertical stacks. There's a lot of advantages to combining this together versus having those all independent runs. This next design example here is a mechanical equipment upgrade on a hotel which had an indoor water park. This facility was originally designed to have electric boiling hot water heaters in this facility, and it was operated there for several years. Based on the energy savings converting from electric to natural gas appliances, the cost saving was huge. But the troubling factor was, while it was easy to configure the plumbing to the new appliances, there was no provisions made in the mechanical room or to run a stack through the building to get the exhaust out of natural gas burning appliances. So we had 3 boilers and 2 water heaters on exact opposite ends of the room, which required us to have a really long horizontal breaching. So this system didn't have enough natural draft. A draft induction fan was incorporated in the system. But even with the draft induction fan in there, to maximize efficiency and to obtain the outlet pressure difference requirements between the boiling hot water heaters, we utilize sequence draft controllers in each outlet of each appliance to maintain flame stability efficiency of each one of those appliances in the facility. And the last design example I'm going to show you is an old college dormitory building done at Boston College. The design criteria for this was to replace existing boilers with new high-efficiency boilers, one used for domestic hot water, other 2 for building heat, not just for this building but other buildings, but not only to run on natural gas, but to be able to run on fuel oil as a backup. So when you start looking at all the different sizing scenarios with various firing rates, using natural gas or fuel oil, and to compound the domestic hot water heating boiler, which would be running by itself in all various ambient temperature conditions, overdraft was very, very prevalent in a lot of scenarios. So we've got a tall vertical stack height, just lowering this in there. Maintaining those outlet pressures on the positive side could have only been done utilizing individual sequence draft control dampers. Kind of sum up, Category 4 operations where we're going to achieve our maximum efficiency. Anytime we start crossing over to Category 2 operation, we're going to lose from our published efficiencies, and we risk flame failures or boil alarms when we do that. Okay, how do I make sure my sizing calculation, my design stuff translates to what the contractor buys and installs in the facility? First and foremost, from an imaging standpoint, I really feel that those sizing or pressure drop calculations need to be done for all systems, all appliances. It's not a slam dunk that the boiler's got a 6-inch or 8-inch outlet that I just run my vent in that diameter and it's going to work. And you're going to want to do it for every manufacturer that might potentially be utilized. It's often for us to work in designing a system. We get final submittals on boiler hot water heaters, and they have changed. And that can lots of times have a drastic effect on the design of our venting system. So you want to match them up and make sure they work, and you want to make sure you do them for all operational conditions. Draft induction fan, if you find out you need it, great. If not, let's use natural draft as much as possible. Outlet pressure control, same thing. Not required on every system we do out there, but it's sure nice to do the engineering work up front, recognize potential issues, and design the solution for those systems before they're installed and have operational issues in the field. And provide detailed system configuration. If we've done a sizing calculation and we know it works based on that sizing calculation, you want to provide a detailed diagram or drawing of that system to make sure that's followed. And if not, we can change things as we're making those design changes. So provide drains in the system, provide draft control if needed. Make sure you've got proper termination, and just make sure that our pressure drop calculation is accurate because it follows the design that we've submitted on the bid documents and that the contractor is going to submit on for final approval. And then last but not least, specification really needs to match the design criteria that we have. Master spec, it does a very poor job of writing a very good vent spec. It includes anything from category 1, category 3, category 4, all mixed into one spec. And if a specification is not tailored for the specific appliances or the specific design criteria that needs to be met for proper operation, it leaves a contractor very confused about what he really needs to bid on bid day. Going to hit on one short topic before I leave. High efficiency venting systems, condensing, produce gallons of condensate in the vent system. And one of the biggest challenges that contractors face is trying to make sure those systems get sealed so the corrosive condensate that's in the vent system doesn't leak out and doesn't cause damage to not only the vent but other items in the mechanical room. So this is a section cutaway, but the industry standard for special gas vent systems or vent systems for high efficiency boilers is a male-female joint connection with an overlap that goes against the airflow. The reason that overlap goes against airflow because as I have condensate being produced out of the boiler and being produced in the stack, I need to drain that back towards the appliance or back to a drain. So by having a male-female overlap, I get the shingle effect of letting that condensate run back against the exhaust flow. The problem with the male-female connection like that is it goes against any design of air duct you would ever do to where you force the flow up against my sealing surface at all times. And if that sealing surface isn't perfect every time, it's going to be a real risk of leaking and forcing not only exhaust gas but condensate past that gasketed surface. It also causes an added loss in the system because I've got a surface now that's not smooth, not consistent diameter of the system, which restricts my exhaust flow. Pressure stack systems for non-condensing systems have been for years half-inch flange connection, so they're not subject to directional flow or taking exhaust flow and forcing up against the sealing surface. We've taken that same design approach to our condensing systems and included a factory-installed gasket on the flanges, so cross-section of our product has no directional implications to it, so it can be mounted away and allows airflow to easily go over our sealing surface one direction and conversely allows condensate to flow back across it to the drain of the boiler without any risk of leakage. And because of that design, we've placed a leak-free guarantee on it for contractors and for building owners. That concludes our presentation today. I know Craig's graciously here tried to answer as many questions as he can. The rest of those questions will come to our inbox, and we will definitely address those. You can feel free to reach out to us at Schebler at any point in time. Go to our website. There's ways you can contact us from there. We're also going to be presenting at the AHRAE Expo in Chicago next week, Monday, Tuesday, Wednesday. We're in booth 2946. We're going to be showing some sequence draft control as well as grease duct system and things like that we do here as well. So feel free to stop by. I appreciate everybody joining in this webinar, and hopefully this information was useful. Thank you.
I do have one question came in, Mike. It's please tell the most common mistake on common venting.
Most common mistake on common venting. Most common mistake on common venting would be not doing sizing calculations accounting for low firing conditions. We see the kind of the thought process. We make sure that the breaching stack are big enough. We kind of use the category 1 or 3 philosophy that, hey, it's large enough we can handle full exhaust flow. But a lot of times it's failed to look at what happens in low firing conditions. Obviously, I've got modulating boilers and I want to take advantage of it. But if my sizing calculation doesn't account for it, I may find myself in extreme negative condition and I start having flame failures with that boiler, and I'm going to probably blame the boiler manufacturer for the issues I'm having with it, when in essence, we didn't put in any kind of draft control when it may have been required.
Does SMACNA standards address or include these issues, or does boiler exhaust land in a different standard? Your
boiler exhaust typically is going to be addressed in International Mechanical Code, NFPA 54 for gas burning. But like I said before, those guidelines don't go through the draft calculation scenarios, don't give us rules that you have to follow on accommodating for high fire, low fire conditions. Pretty much everything I've read in code and standards really falls back to engineered systems and design practices that are satisfactory to the boiler manufacturers. So, no, I mean, really pretty much it's going to be left up to the boiler manufacturer and the venting manufacturer and the engineer to design this system and make sure it's going to function.
But somebody asked earlier about being able to vent category 4 horizontally through the wall, which I think you touched on that. That's basically comes down to the more important with the sizing.
Right. Anytime we do a sidewall termination, we obviously have to take a close look at it because we don't have much natural draft available. Individually venting, it seems to works better with that than trying to common vent. Couple real concerns with sidewall venting. It's not so much sometimes even the sizing calculation. It's what is the impact of the exhaust coming out the side of the building. Now I've got exhaust gas, which is low temp, doesn't have a lot of buoyancy to it. It's got moisture in it, and I've seen several cases where they've dumped exhaust out the side of the building, horizontal termination, and the entire side of the building is wet or got freezing ice from it from all the condensate rising up. And you also have to be real careful of where the intake is on those systems as well. The minimum set distance, and I can't recall off the top of my head what that is in code, but maybe I would be close to far enough if I've got any prevailing wind or chances to swirl around and bring it right back in the intake, because that exhaust plume is pretty low temp and has a moisture in it, which to me really affects its ability to rise and get out of the area that it's coming out of the building.
I'm having trouble being able to scroll here real quick, but another one was, is the sequence draft venting system that we have approved by various boiler manufacturers?
I am going to say yes. We've worked with several boiler manufacturers, several major boiler manufacturers. We've had success with various manufacturers. So the number one thing we get back from boiler manufacturers is, can you control my outlet pressure inside the range that I've designed it for? And really in this case, if we've designed the system that responsibility is going to fall solely on us. Obviously, we can't control things like, enough makeup air wasn't designed in the room so the boiler can't operate, things like that. But on the exhaust side, we design the system, and we sign up saying we can retain those outlet pressures. I'm sorry, now, a vast majority of the boiler manufacturers are going to be and have been okay with our sequence draft control design.
There's a lot here I'm going to have to probably answer later. They want specific examples. But got a couple here about ice forming tops of the vents. I don't know if we've had experience with that. 3 or 4 questions about that.
Okay. We'll answer those. I mean, I've seen that. I think that's why the biggest thing you're seeing now is condensing systems always typically used to utilize a rain cap. Thought process, we didn't want a bunch of rainwater coming down in a stack system that we had to contend with. That design has kind of crossed over into a lot of condensing systems where we put a stack cap on there. But the stack cap is just a way for us to collect ice and moisture on, which can be a real problem. Several boiler manufacturers even don't allow stack caps for that reason, because our system can handle moisture anyway. So typically, not having a stack cap on there would typically cure any issue as far as having the exhaust collect and freeze and block the flue passageway.
I was getting a lot of questions on how we're coming up with these calcs, whether it's available or not. Probably the best way to get to that is to contact us.
Yep. We'll address those independently on how we do our calculations and what information that we can directly provide you. Well, again, I want to thank everybody for participating. Feel free to reach out to us at any time. Hopefully this almost hour-long webinar was beneficial, and hope to see some of you at the ASHRAE show. Thank you.